Hello everyone, welcome back to the latest lecture session. After discussing water treatment or the conventional water treatment related aspects, we moved on to looking at some of the recent developments which are taking place, right, which are applicable to water treatment and some of which are also applicable to wastewater, right. In that context, we looked at membrane process and mentioned that we discussed about ultrafiltration and microfiltration, and there the principle was primarily about exclusion based on size. And then I believe we looked at ion exchange, right, adsorption and then ion exchange. Next class is relevant to nanofiltration and osmosis or reverse osmosis, where we look at removal of dissolved ions too, right. So, nanofiltration and RO or reverse osmosis is what we will look at, and with that we will end or wrap up water treatment related aspects, right. So, just a bigger picture with respect to water, right. If we want to remove suspended solids, we looked at that, sedimentation tanks, we looked at disinfection for pathogens, right. So, depending on our requirements, sometimes we will need to remove or look at applications of membrane filtration. So, that is something you will have either before or typically before disinfection or after too sometimes, but typically before disinfection, or ion exchange maybe in industrial process and such, let us say, right, or in the context of wastewater. So, again these, as you can see, are not usually used. In general, we look at these two aspects for the conventional water treatment, but now I guess due to industrialization and ever increasing stress on water, we are having to look at ion exchange, membrane process, adsorption and so on and so forth too. So, let us go forth nanofiltration. So, until now we have looked at conventional filtration, microfiltration and ultrafiltration, right. And then I guess we are now going to discuss nanofiltration and reverse osmosis. Obviously, what do you see here? We see that the sizes that we are talking about are decreasing drastically. Each one is 10 times less than the preceding one. So, you can understand the sizes that we are talking about. And nanofiltration, why did that name come about, or how did it come about? Well, the sizes were 1 nanometer, right, and that is why people started calling it nanofiltration. Again, let us move forth. So, what is it that nanofiltration can remove? Again, the size of the pores, as you can see, is 1 order of magnitude lesser than that for ultrafiltration, typically anyway. And what can it achieve, or what can it remove? It can remove dissolved organic matter and the divalent ions, let us say for example calcium and magnesium, which are of interest to us. And then reverse osmosis, it can remove even the monovalent species like sodium and Cl minus, right, or chloride. Again, as you can see, different sizes and different types of treatment. So, depending upon what you want to achieve, you will look at that. Reverse osmosis, you would have seen this, or most water treatment or household units have this, right, but it is not really necessary depending upon where you are living at, obviously, but again we will look at that later, right. So, overview of membrane process, what have we seen? Pretty effective, efficiency is pretty good, but slow rate of transfer across the membrane and coupled with high pressure drops, right, and thus we needed a relatively higher surface area, but because they are packed relatively well, or per unit volume you have considerable area, so that can be achieved, let us say, right. Again, we are trying to separate the colloidal and dissolved solids that are much smaller, right, than those that are removed by the filtration process. That is a generic aspect. So, with respect to nanofiltration, as mentioned earlier, we are trying to remove, or we can typically effectively remove divalent anions or cations. Monovalent relatively poorly removed. So, that is one aspect to keep in mind. So, operational challenges, as in when I am using nanofiltration, right, either in an industry or for water treatment, what are the challenges that I will face? So, scaling and fouling of the membranes. What is this fouling of the membranes and what is the scaling of the membranes about? For example, think of this, we know that calcium can precipitate out, right, or let me write it as the dissolution reaction, this will be in equilibrium, right. So, near this membrane surface, especially this will be relevant to RO, but let us discuss this now too. Near the membrane surface, if the concentration of your relevant ions which can precipitate out is really high. What does that mean? So, for this particular reaction, the concentration is relatively high, right, at least for these products. So, the backward reaction will be feasible, right, and you can have precipitation on the membrane. So, that can lead to scaling of your membrane, and fouling of your membrane, you will have either organic matter or organic matter, typically natural organic matter, which can be adsorbed onto the membrane surface, and that will lead to fouling of the membrane. What issues is that going to lead to? Rejection, right? Rejection is going to be an issue, and also greater pressures are required for the relevant water flux that you want to achieve. So, that is an aspect to consider, right. So, let us move on. Biofouling. Here we have undesired development of microbial layer. So, initially you might have some microbial attachment, and once the conditions are such that the microbes can thrive, now you will have colonies being formed, microbial colonization, and then microbial growth, right, extracellular polymeric substances, right, again microbial attachment, colonization and growth. So, this again will lead to biofouling, and again issues with respect to rejection and higher pressures, right. These are the aspects that need to be considered or looked at. So, what are some of the ways to look at this? So, we are going to have to employ pre-treatment. One aspect is to prevent scaling. So, if I want to prevent scaling, I can either remove the ion that causes scaling, right, before it reaches the membrane of interest, nanofiltration or the RO membrane, or I can inhibit crystal growth. In precipitation, there are different stages. One is nucleation, the first step, and the other one, next one will be crystal growth, right, and then agglomeration and so on and so forth. So, you can look at various ways to minimize crystal growth. One is obviously concentration, one is surface area, turbulence and such, let us see, right. So, that is one aspect to keep in mind. So, you can also filter out the particulate matters to prevent deposition on the membrane. Obviously, this is relevant to organic foulants, let us say, natural organic matter and so on and so forth. Or we can also add chemicals. This is typically widely used in industries, anti-scaling agent for scale control, as in you want to prevent precipitation, right, you want to prevent precipitation. As we saw earlier for precipitation, I think where is that? Okay. So, if I add a ligand that makes calcium more soluble and free metal or free calcium, the solution is less, then this reaction will not proceed to the left, right. Even though the calcium total is still the same, the proportion of calcium total which is in the form of Ca2 plus will be relatively less, and that is what I am concerned here, right. So, that is what we can take care of by adding anti-scaling agents, let us see. Or obviously, when you have metals or such, and you know that at relatively higher pH most of them can precipitate out with the hydroxide or the relevant ligand, you can control the pH as required, let us see. So, sulfuric acid, or depending upon requirements for increasing the pH, you can add caustic soda. So, pH and anti-scaling agents. So, desalination, right. So, you have saline water, relatively high ionic strength, relatively high salt concentration, and you want to remove that, remove these salts concentration. So, how do I do that? First, why, I guess, why? Well, India again along the coast, we now the people are in considerable water stress, but they see water all around. So, that sea water can't be used because obviously high ionic strength, high salt concentration. Even if you take that water, you know, it will not serve the purpose for which we take the water, let us see, right. You are going to feel more thirsty if you what do we say, take water, it is osmosis in a way. Again, let me not go there. So, we need to desalinate that water, right. Why is it? Because we need water, we need more water requirements, or every day we are increasing, or we have ever increasing need for water, we are not managing water well, right. So, let us look at what we have. So, need for more water, and what are the types of raw water? Sea water or brackish water, which is relatively less ionic strength, again sea water and brackish water. So, different types. One is thermal distillation, this is something that people would have come across. Distillation, typically energy intensive, you need a source of heat so that you can convert the water into water vapor, and then as you pass it through, though the relevant salts are not going to be converted into the gaseous phase, they are going to stay in the stay as solid, right. So, the vapor can later be condensed and used for water. So, distillation, but the conventional way, it's too costly, too much energy. So, what do they try to do? To my understanding, they try to decrease the vapor pressure, so that even at relatively low temperatures, right, the water can be boiled. So, that is where I believe the efficiency of the system comes into place, but in general this is not widely used, at least for desalination. That is one aspect to keep in mind. And as mentioned here, it is multi-stage process, typically temperature and reduced pressure. That is something that, why do we want that? We want to look at decreasing the vapor pressure. Again, what is the key aspect? Because I want to reduce the energy consumption. If not, I need to provide more energy for that heat of vaporization, let us say. So, that is the relevant aspect here. So, types of process, and one was distillation, right. The other one is electrodialysis, right. You might have heard of dialysis, right, with respect to, I think, kidneys and such. Well, we are trying to mimic that here in a way, but unlike nanofiltration RO, where the driving force is pressure, here it is electrical voltage, right. So, that is something to keep in mind. We are going to, what are we going to do? We are going to apply a direct current voltage, right, and that will bring about a movement in the relevant ions. We will look at the picture, right. How is it going to happen? Negatively charged ions move towards the positively charged anode, and positively charged ones towards the negatively charged cathode, let us see, right. And obviously, the issue is, if we have electrically neutral substances, then obviously they will not be removed. Earlier it was in vogue and then fell out of favor after RO and such, but again I think it is coming back into the picture, let us see. So, what are the key aspects for electrodialysis? As we mentioned, we have electrodes, and then we are going to apply a voltage such that positive ions move towards one, negative ions towards one, and then you will end up with a clear, not clear, relatively, water that is free of charged species, let us say. But obviously, you want to have, you will need to have electron neutrality, right. You can't end up with water that is charged. Yes, let us see how that is brought about. So, you are going to have three major aspects here: ion selective membranes, and obviously, I am going to impose an electrical potential, right. And the key aspect is that the ions are going to migrate through these ion selective membranes, let us see. So, let us see how it is done. So, here is a picture here. Note that we have C stream and D stream. D stream is the one that I am collecting for my product, and C stream is the one that is like the concentrate, let us see, or the reject, you can think of it, right. And E stream, it can be similar to the same water as the one that you are trying to treat, right. Again, that is for charge balance related issues, if I am not wrong. So, what do we have here? We have the negatively charged electrode and positively charged electrode, anode and cathode, right. So, once I apply a potential, the relatively charged species are going to start moving to the oppositely charged electrode, let us see, right. So, for example, sodium, I guess, will try to move towards cathode, sulphate will try to move towards anode, right. So, that is one aspect to keep in mind. So, what are the roles of these ion selective membranes? As in, they will only let either a cation go or only an anion go through them, right, or migrate through them. Let us look at this. This is, I guess, specific to cations, or it is not going to let cations through. This is specific to anions, this membrane, it is not going to let anions go through. Let us follow the streams here, right. So, here is my water that I want to treat. As it goes along, once the potential is applied, the sodium will try to move towards the cathode, right. But this membrane here will only reject or prevent migration of anions. So, sodium cation positively charged can go through that, but then at the end of the day it will not be able to migrate through this particular ion selective membrane. So, we will end up having relatively high concentrations of sodium, but water has to be electron neutral. So, again, that is why you see that SO4 2 minus from this E stream moves into this particular stream here, and then more or less you will achieve electron neutrality, let us see, right. But what is happening to this particular stream that I have here? So, Na plus was removed, right, while migrating towards the cathode, and Cl minus while migrating towards the anode will be removed similarly. Here Cl minus can migrate through this cation specific membrane, right. So, Cl minus will pass through that, but not through this particular membrane, right, and now there will be an increase in concentration of Cl minus. So, thus you are going to have alternating, membranes or ion specific membranes, and you are going to have potential, and you are going to have a stream where the concentration of the ions is relatively high, that is the reject stream, and another stream where the concentration of the ions that you want to remove is relatively less. So, some aspects, when will this work fine? This will work fine when you have high concentrations of the relevant charge species, and your final product that you want is not such that it requires very low concentrations of these charge species, then it works relatively well. If not, I guess it starts getting relatively costly, right. So, better when the concentrations are high and we do not need low product concentrations, leading to less energy loss to force ion flow, that is the relevant issues. But as mentioned earlier, even though not very common now, they will probably make a comeback. So, reverse osmosis, you would have seen this in your household water purification systems. In general, whenever you collect the water from your RO systems at home, keep in mind that not all systems have RO. If you know the kind of water that is present in your locality, and by understanding this course, you can look at whether you are fine with maybe an microfiltration membrane and maybe an activated carbon filter and maybe a UV, let us say, right. You can play around with that, but again everybody or the company guy tries to sell you RO because it is relatively costly, I guess, and he can make more money off it. But I would urge caution, look at what is the quality of the water that you have and what is the acceptable limit, and then go ahead and choose it. Why is that? Because first you need to apply considerable pressures, that is one aspect, and more importantly you would see that. So, again this means that the costs are relatively high, and also the membrane cost itself is pretty high whenever you have to change this membrane, right. We know that fouling takes place, different types of fouling, we just looked at that, biofouling, organic fouling, scaling and such, right, and some of the scaling is irreversible too, right. So, then you have to change the membrane, if not water will not pass through and you will have very little water coming through for the feed water, right. So, again these are the aspects that need to be looked at because of the cost. And also more importantly, note that whenever I have RO system here, let us say, and I am taking the water here, you will see that there is a reject stream, right, and there is considerable reject water that goes out into the sink. So, for each, depending upon the system, how old the membrane is, right, or how much fouling has occurred on the membrane, you are going to see considerable reject water coming out. So, for every liter, depending on how old the system is, you can maybe reject up to 2 liters or so of water, but again that depends obviously. So, you need to consider these aspects regarding water wastage and such, right. Let us move on. So, what is it that we are talking about? Reverse osmosis. So, what is this osmosis about? We will look at the figure, but let us just look at the written statement that we have here. It is the movement of water, keep in mind it is the movement of water, not of the relevant molecules or the ions. Where does it move from? It moves from higher concentrated solution to lower concentrated solution, right. Why is that? Like diffusion, increasing the entropy, making the system more similar, right. So, for example, if I have highly concentrated salt solution here and relatively less concentrated solution here, relatively high chemical potential here, right, and so I want to achieve equilibrium, that is what the system tries to achieve. This is from thermodynamics more or less. So, but for now let us limit ourselves to chemical potential. To achieve the same potential, what is it that water is going to do? The water is going to migrate from this relatively low concentration zone to the one with high concentration zone, so that the concentration in this high concentration zone also comes out to be low enough or relatively enough or low enough such that it is similar to the one in the low concentration zone, right. So, again that is the aspect we are talking about water. So, reverse osmosis, this is what usually happens, but we obviously do not want that. We want reverse osmosis, right. We want movement of water again from low concentration to high concentration, but this does not happen in nature, right. That is why we want to impose a pressure. This is what leads to the cost, right, and this has to be applied such that it overcomes the tendency for osmosis. And how can I understand that pressure? So, it is osmotic pressure, it is the pressure required to stop the osmotic flow from one solution or from the solution to pure water, let us see. So, let us understand via the two figures that we have here. On the left, I guess we see osmosis, right. So, what do we have here? We have relatively high concentrated water here, relatively low concentrated water with respect to the relevant salts or such, let us say. So, to achieve the same potential, the water is going to go from here to here. So, over time the concentration here is going to increase and concentration in here is going to decrease to a level such that both are at the same concentration. But what is it, and okay, so this is the final product, right. So, this is what more or less happens, water will go to here and now the concentration here and concentration here is the same. But how will this help me? It does not help me, because now the concentration is more or less high throughout all the what do we say, water systems here, let us say, right. So, here I am going to apply a pressure to negate this, right. So, reverse osmosis, this is osmosis. So, we are going to look at osmosis. So, I am going to have the feed and I am going to apply the pressure. So, there has to be a driving force. In general, if we look at classes and such, people or students will do what is relatively easier for them. So, if you want to make them do something, or the majority of the students, you have to force them to do that. So, you can think of the driving force in that manner. So, it is the pressure that you are going to apply, let us say, right. So, in that way I guess you are going to have permeate and you are going to have the concentrate or the reject, where the concentration of the relevant ions is going to be relatively high. Let us look at the relevant picture. So, here you can see diffusion. So, if we remove this, okay, what do we have here? We have concentrated solution here and relatively pure solution here, pure let us say, and concentrated, fine. And if I remove this removable partition, so you are going to have movement of the salt ions. But I guess because of mass transfer and mass balance, you need to have also flux of water in this direction, right. So, that is an issue. But with respect to this membrane, which will not let molecules go through. So, that is why let us say it is the RO membrane, semi permeable membrane, only water will be allowed to go through. So, what is going to happen here? So, we are going to have concentrated solution here and pure water here. So, to achieve the same potential, right, what is it going to happen? The water is going to go in this direction. That is why you see this particular difference in the relevant pressure. But now I do not want that to happen. So, I have to apply this level of pressure source, and then I will see to it that the concentrated salt solution, water from the concentrated salt solution will move towards the pure water, right. So, now I will have more of the pure water, right, while I will have lesser of more concentrated water. So, that is what we are trying to achieve here, right. Let us move on. So, theory and such is fine, let me not go into detail because this is a UG class. So, what do we said, water flux depend upon? Flux is mass per area per time, typically you can look at the units and understand that in general. So, this is the transmembrane pressure, which is the case for every different kinds of membrane, and this is the one that deals with osmotic pressure. For solute, let us say, right, solute flux, I guess it depends upon the concentration gradient, right. So, let us see what we have: volumetric flux of water, transmembrane pressure, and difference in osmotic pressure between the feed and the permeate. So, that is the aspect here. So, mass flux of water, well, okay, concentration gradient across the not water, I guess it should be solute, concentration gradient across the membrane, right. Cp is the concentration of solute in the permeate, right. Cp is the concentration of solute in the permeate. So, these are general aspects here. So, operation parameters, this is similar to what we looked at earlier, but let us look at two variables that we are going to look at. I believe we looked at this in the concept in the when we are discussing ultrafiltration and microfiltration too, right. So, here we have recovery, right, we have permeate and we have feed. So, feed is what I am putting in, permeate is what I am going to use or is useful to me, and retentate, right, or the concentrate or the reject is QR, let us see, right. So, water recovery is QP, this QP by QF, QP by QF, right. So, here if the water recovery is high, that is good, but after considerable operation of your membrane and fouling of your membrane, this recovery is going to decrease, and then your reject water flow is going to be relatively high. So, that is something to keep in mind. That is with respect to the water. So, again as I just mentioned, the limitations are due to increased concentrations of ions in the concentrate, right. Osmotic pressure requires or increase in applied pressure, right. This is the case especially with seawater. Osmotic pressure leads to an increase in the applied pressure, right. and that means again you are going to have coarse. So, chemical scale fouls membrane, for example, as we mentioned earlier in the case of nanofiltration, if you have calcium, right, and I guess this can be reversed because of pH, you can bring down CO3 2 minus concentration and such, but CaSO4, BaSO4, these lead to irreversible fouling. That is one aspect to keep in mind, right. This is reversible fouling, this is irreversible fouling. Again, why does this or how does this occur? As we mentioned, this is the membrane. So, now here we have relatively low concentration of the relevant ions, but here the concentration is very high, right. I am just using a star to denote that. So, if the concentration is very high, then the conditions for this particular reaction to go forth are favorable, right. So, that is why even though in the bulk liquid solution the concentration of Ca2 plus is not high, near the membrane, right, membrane surface, the concentration will be high enough such that you can have precipitation of the relevant metals or such, right. That is something to keep in mind. So, solute rejection, right, rejection, what is rejection? Rejection is equal to Cf minus Cp by Cf, right, feed and permeate, or it is 1 minus Cp by Cef, right. Higher for, this is with respect to the concentration of the relevant what do we say, molecules, right. So, higher for highly charged molecules and higher for larger molecules. So, you can obviously understand that if it is relatively charged and larger, I guess it is relatively easier to reject those particular compounds by RO. So, typical RO facility, this is called a stage, an RO element and such, but this is what it typically looks like, let us say, right. So, let us look at different kinds of RO. Okay, before that, what kind of RO are we looking at? So, membrane material, two widely used, one is the cellulose based and one is the polyamide based. So, this one is more hydrophilic, this one is more hydrophobic, right, and this one though can degrade over time, right, because it is cellulosic material, but this one will be very reactive towards chlorine. So, if there is any chlorine or such in water, that is going to cause considerable issue to this particular polyamide. So, let us see cellulosic acetate, very common, but the issue is that it is not what we say tolerant to temperatures above 30 degrees centigrade, and it can hydrolyze depending upon extreme pH, that is one aspect. So, it is also obviously because it is cellulosic material, right, cellulosic acetate, it is susceptible to biological degradation and also this free chlorine too, right. So, that is one aspect to keep in mind. Polyamide generally resistant to biological degradation, right, and works over a wider range of pH and does not hydrolyze in water, but again very susceptible to chlorine attack, let us see, right. So, let us move on. Properties of RO, membrane configuration, let us see. One is spiral wound, the other one is hollow fiber. Typically spiral wound, we looked at this in the context of I believe ultrafiltration and microfiltration, right. So, spiral wound, let me not read it out, let us look at the picture. Again, as you can see, typically 1 meter long elements with 0.3 meters in diameter, let us see. As can be seen within a 1 meter long element, the area available would be around 30 meters square, let us see, right. So, that is something to keep in mind. So, what is it that we typically have or what happens in a spiral wound membrane? This is what you would typically see in your household RO systems too if you want to open it up. So, my feed solution is coming in, but note that my permeate or the water that I want to use is collected in the center, let us see. So, right, how is it that it comes out into the center? So, it has to take a spiral path, let us say, right, like this, it has to go through these elements and end up here. So, what is it that we have? We have the outer wrap, fine, that is not a big deal. This is permeate collection, right, where permeate collects, and this is the membrane, yes, and membrane flows through the or the permeate flows through the membrane to permeate collection tube. This is the permeate collection tube. So, during this it is cross flow more or less, right. So, that is why it is also better in the to avoid scaling too, right. So, that is one aspect, and also from between one membrane to the other you are going to have this feed channel spacer, let us say, right. Feed solution, this is the concentrate or the reject. So, it is going out in this way, and the one that passes through the membrane, you know, this spiral membrane, let us say, or spirally wound, pardon me, will end up in the permeate, right. That is something to keep in mind. So, again a different kind of figure to understand it. So, water, then the relevant membrane, because it is so thin, it does not have its own strength. So, it is cast on fabric backing. So, again porous permeate carrier, this is where the permeate goes through, and again membrane, right, and again as I mentioned earlier, water and flow spacer. Again all this will end up in the central permeate water collection system, let us see, right, or the tube. Let us move on. So, if you cut open your homemade RO units too, this is what it should or look like similar, or this is what it should look like, the different membranes and such that we looked at. What are we seeing in the next picture? We are looking at this porous permeate carrier, we are certainly looking at the membrane, and we are also looking at the water and flow spacer, right. These are the aspects that we are looking at. So, again you can look at this picture. Again this is from McKinsey's the student presentations, right. Let me move on. So, again it is going to take a spiral path, it meaning the water, and reach your collection tube. And hollow fiber not very much used, right. Let us just look at that particular aspect. But where is it used? It is used for desalination of seawater in the Middle East, I guess, but in general people are moving away from hollow fiber, let us see, right. Again hollow fiber, this is what it looks like, and you can see that it is not a spiral or such. So, the pre-treated water comes here and permeate goes through here, and you can see that this concentrate I guess leaves this system here, right. At least certainly you see that it is hollow fiber, let us say hollow fiber. So, what are the limitations in RO, let us see, right. As mentioned, right, you will see that you need to apply pressure otherwise to overcome this osmotic pressure, right. So, that itself is a need for or considerable what do we say drain on the resources. So, that is one reason why the industries at least in India do not prefer to go for RO. Other reason is that before RO, if you do not have the well functioning microfiltration or ultrafiltration system, which does not remove those products which can lead to scaling or fouling of your RO membrane, what will happen? You have to change your RO membrane pretty frequently. And also for RO you need to add anti-scaling agents or relatively look at what is it now, removal of these hardness, not hardness, the scales like CaCO3. This is reversible with pH, right. CO3 2 minus, if I bring it down the pH, HCO3 minus or H2CO3, right. But if I have the solid precipitated out as CaSO4, right, you know that at almost all the pH range SO4 2 minus will stay as SO4 2 minus. So, it is difficult to remove this. So, this is irreversible fouling and reversible fouling. So, these aspects also need to be taken into account when you are looking at operating the RO, let us see. So, the costs are pretty high with respect to operating the RO and also with respect to changing the RO membrane, pretty high. And another aspect is you have the reject, right, or the concentrate. So, the brine disposal cost, what to do with this? Again, you can have a multi-effect evaporator or landfill or such. So, again brine disposal costs are again considerably high, let us see. So, with that we are done with water treatment. So, from the next session we are going to look at the aspect related to the sludge, let us say, or the solids that we have collected. As in sedimentation tank, we are going to collect solids at the bottom. As in again in the secondary sedimentation tank in biological wastewater treatment, we are going to collect sludge at the bottom. What do we do with them? We can't just dispose them, right. So, that is what we are going to look at in the next couple of sessions and wrap up this course. Thank you.